Welcome to CSC 201, Lesson 4.1. The definition of even and odd numbers. So I've written these in symbolic notation. I'll read them out in English words. So it says, for any integer n is even if and only if n is twice an integer. N can be written as twice some integer. And n is odd if and only if n can be written as twice some integer plus 1. So using these definitions, is 0 even? So can 0 be written as 2 times an integer? Yes, 0 can be written as 2 times 0. So even. If a and b are both integers, is 6 times ab even or odd? Well, 6ab, we want to know, can that be written as 2 times an integer? Because that's the definition of even. Otherwise, it's odd, 2 times an integer plus 1. So 6ab can be written as 2 times 3ab. And 3ab is an integer because the integers are closed under addition, subtraction, and multiplication, which means if you add 2 integers, you get an integer. If you multiply integers, you get an integer. If you subtract integers, you get an integer. It's not true for division. Dividing 2 integers doesn't always give you another integer, but addition, subtraction, and multiplication work. So 3a and b are all integers, which means 3ab is an integer. So this is 2 times an integer, which tells me that 6ab is even. 8r plus 7, is it even or odd? So I want to know, can it be written as 2 times an integer or 2 times an integer plus 1? So let's try doing 2 times an integer. So let's see what happens. So I have 8r plus 7. I'm going to try to factor out a 2, but the problem is that 7 can't be written as 2 times an integer. So when I think about what to put in these parentheses, I would have to put a 3.5 here, which is not an integer. So I'm going to put a 3 so that I have 4r plus 3. Now when I distribute that, you get 8r plus 6, right? So not quite this. 8r plus 6 is not quite 8r plus 7. I still need to add 1. So this is 2 times an integer. 4r plus 3 would be an integer, plus 1. 2 times an integer plus 1, that is odd. Let's talk about the definition of prime and composite numbers now. For any integer n with n bigger than 1, n is prime if and only if. For all integers, if you can write n as the product of any of 2 integers, then the one of those integers must be the original number n. Okay? No matter how you factor it, so if you can write n as the product of 2 numbers, one of these numbers must be n, and then the other one would have to be 1 by default. And then n is composite is the negation of n equals prime. It means n is composite if and only if there is an r and an s. There are integers so that you can write n as r times s, but neither r nor s is equal to n, and neither r nor s is equal to 1. So using these definitions, let's try to answer each of the following. Is 1 prime? The answer is no, because at the very beginning, we said these definitions only apply to integers greater than 1. Definition only applies to numbers bigger than 1. Is 2 prime? Well, the only factorization for 2 is 2 times 1. There are no other integers we can write 2 as the product of, so 2 is prime. Now, if r is an integer, is r squared plus 4r plus 3 prime, or composite, or neither? So r squared plus 4r plus 3 can factor to r plus 1 and r plus 3. Now, for r squared plus 4r plus 3 to be prime, that means that one of these numbers has to be the original, and one of these numbers has to be 1. So it is possible to make one of these factors 1 depending on the choice of r. So is this expression prime, composite, or neither? It depends on the r value. Okay, if r equals 0 or r equals -2, right? When r equals 0, this factor would be 1. And when r equals -2, this factor would be 1. So there are two r values that would make this prime. Otherwise, it's composite. Recall that an existential statement of the form "there exists an x in D such that Q of x" is true if and only if Q of x is true for at least one x in D. So these are these kinds of statements are relatively straightforward to prove, in that we just have to find an x, like find one x that makes Q of x true. You could also provide directions for finding an x rather than actually finding it. You can provide directions for your reader. Either of these is called a constructive proof of existence, where you just show proof that you can find one of these x's. Okay, so let's prove each of these statements. There exists an integer n such that 2n plus 1 is prime. So we just have to find one. To prove that this statement is true, we just have to find such an n. So this, let's consider n equals 1, right? So 2 times 1 plus 1 is 3, and 3 is prime. Check. We proved it. We found an n equals 1, such that 2 times n plus 1 is also prime. Okay, statement B. There are real numbers a and b such that a plus b squared equals a squared plus b squared. So we know that this is not true for all a and b, right? This is a very common mistake that students make in an algebra course, is assuming that this is always true. But are there any numbers that make this true, right? This is just an existence. There are some real numbers, a and b, that make this true. So let's consider a equals 0 and b equals 1. So a plus b would be 0 plus 1 squared. Does that equal 0 squared plus 1 squared? And we get 1 equals 1. Check. There is an a and a b that can make that true. Sometimes finding the exact x that can make Q of x true is too hard or time-consuming. In this case, we can use a non-constructive proof of existence. We can try to prove something exists without actually finding it. So an example of that is the intermediate value theorem from calculus. So prove that there exists an x in the interval 0 to 1, such that x to the 71 minus 2x to the 39 plus 5x minus 0.3 equals 0. So if we consider this a function f of x, let's analyze the sign of f of x at the beginning and the end of the interval. So f of 0, if you plug 0 into that function I underlined there, you get negative 0.3. And if you plug in a 1, you get 1 minus 2 plus 5 minus 0.3, which is 3.7. All right, so at the beginning of the interval, at 0, the function is negative. And at the end of the interval, at 1, the function is positive. So if I were to try to draw this function, I know a couple of points now. So I know at 0, my function is negative 0.3. And I know at 1, the function is positive. It's 3.7. Okay, and what I know about f of x, this function that I underlined here, is that it's a polynomial. And polynomials are continuous. So if my function is continuous, that means I have to be able to connect this point to this point without picking up my pencil, which means I'm going to have to cross that x-axis at some point. So to write this out, I can say since f is continuous and f of 0 is negative and f of 1 is positive, f must cross the x-axis between x equals 0 and x equals 1. So wherever it crosses, that's the solution to f of x equals 0, right? So we know that there is a 0 somewhere between 0 and 1, but we proved it without finding it. So that's a non-constructive proof of existence. To disprove a statement means to show that the statement is false. So we're going to consider the question of disproving a universal statement of the form for all x and d, if p of x, then q of x. So to show that that statement is false, we could equivalently show that its negation is true. So let's look at its negation. The negation of a for every quantifier is a there exists. So this says there exists an x in D such that not P of x implies Q of x. Right? So I'm thinking about this negative sort of like distributing. I'm saying distribute to here, and the for every becomes a there exists. And then I'm putting a not on the conditional statement, if P of x, then Q of x. So I'm just putting a not in front of that. So you do not that, and then the negation of a conditional, you'll recall, is the only way a conditional can be false is if the if part is true and the conclusion is false. The then part is false. So this would say such that P of x and not Q of x. So that's the negation. So if my goal is to disprove this statement, I have to prove this statement. Okay. So if I want to disprove that for all x something is true, all I have to find is a single x, show that there is one x such that it's not true. And finding that x is called a counterexample. So we can disprove a universal statement by providing a counterexample. That is, finding an x for which P of x is true and Q of x is false. So we're going to disprove the following statements by finding a counterexample. So sometimes this takes a little trial and error to find your counterexample. The first one says for all n in z, so for all integers, if n squared plus 3n is even, then n is odd. So what I need to find is an n that is even and n squared plus 3n is even. So I need the p part to be true and the q part to be false. So I need n squared plus 3n to be even and n to also be even. Okay, so I just have to find an n that makes this an even n that makes this true. All right, so the first even integer would be 2. So let's see, if I plug that in, I get 2 squared plus 3 times 2 is 4 plus 6, which is 10. And I found my counterexample. That's it. Okay, so I found an even n that makes this true. Okay, so this says for all n and z, if n squared plus 3n is even, true, then n is odd, false. Okay, so there's my counterexample. Next statement. For all real numbers a and b, if a squared equals b squared, then a equals b. So we have to find a set of real numbers a and b. So we just have to find it one a and one b, so that a squared equals b squared, but a does not equal b. This would be our counterexample. So here, positive and negatives are going to work for us here, because when you square a positive, you get a positive, and when you square a negative, you get a negative. So if I choose a equals 1 and b equals -1, a squared plus b squared is -1 squared. Oops, not plus. Sorry. Does a squared equal b squared? So a squared equals b squared. So we would have 1 squared. Does that equal -1 squared? Yes, they both equal 1. Okay. But does a equal b? No. A is 1 and b is -1. So we found the existence, we found an a and a b, such that a squared does equal b squared, but a does not equal b. There's our counterexample. So we've proven existential statements, and we've disproven universal statements, but the vast majority of mathematical statements that we want to prove are universal. So these are tougher than proving existential statements, because in existentials, you only have to find one time the statement is true. You can just go searching for a value that works. But to prove a statement of the form, for all x in D, if P of x, then Q of x, we use the method of direct proof, right? It's hard to do by exhaustion. It's hard to show that it's true for all x's if your domain is infinite. Like if you're trying to show something is true for every integer, that's hard to prove by just doing examples. In fact, it's impossible to prove by example, because you can never show every single integer that makes it true. So our method of direct proof consists of 3 steps. Express the statement to be proved in the form for every x in D, if P of x, then Q of x. This is often done mentally, but for these first few, I'll write it out. Consider this problem that we want to prove that the sum of any 2 even integers is even. The first step is to write this statement using more formal language. Prove that the sum of any 2 integers is even. So I would say that for all a and b in Z, so for all integers a and b, if a and b are even, then a plus b is even. So I just wrote it out a little more formally. So that's step 1. Okay, step 2 in direct proof is to start the proof by supposing x is a particular but arbitrarily chosen element of the domain, for which the hypothesis P of x is true. So we often abbreviate this, suppose x is in D and P of x. So we are going to suppose a and b are elements of the integers, and a is even and b is even. Okay, so you suppose that the if part of your statement is true. So we're going to assume this is true. And then step 3 says show that the conclusion Q of x, that a plus b is even, is true by using definitions, previously established results, and the rules for logical inference. So step 1, rewrite using formal language. Step 2 is suppose that the hypothesis of your conditional is true. So we're going to suppose we have 2 integers that are both even. Okay, step 3 is to use definitions, theorems, and the rules of logical inference to prove that this part is true, that A plus B is even. So the definitions we have at our disposal for this would be the definition of even and odd. So we'll use those. All right, so we have assumed that A is even and B is even. So A is even means A can be written as twice an integer, okay, for some K in the integers. B is even means B is twice an integer. Not necessarily the same integer, because A and B aren't necessarily the same number, right? A is even and B is even, but they're not both 2 times the same integer. So I have to use a different letter here, 2J, for some J in the integers, okay? It's possible that K and J are the same, but we're just saying that A is even and B is even, and they're not necessarily the same even number. Okay, so we've used those definitions of even. We can say, thus, A plus B by substitution is 2K plus 2J. And then we could factor out a 2 from each of those terms. So 2 times K plus J. Now, K plus J, that's an integer plus an integer, which we know is an integer. So we can just say, since K plus J is an integer, A plus B equals 2 times an integer, and thus, and thus A plus B is even. So for number 15, we're going to set up a proof of the following statement by finding a starting point and what we need to show, or the result to be proved, as your textbook says. We're not actually going to write the proof, which we can't because we don't know what any of these things mean. What's a complete bipartite graph? And what does it mean to be connected? If we wanted to actually prove it, we would certainly need to know what those things are. But just to set up a proof, to know what its structure would look like, we can do that without knowing those definitions. So we know, where do we start? Our starting point would be to write it out in formal language. It says that for every graph G, if G is complete and bipartite, then G is connected. Okay, so step one, restate. Step 2 is to suppose that the if part is true. So we're going to suppose G is a particular but arbitrarily chosen complete bipartite graph. Okay, so that's our starting point. Our step 3 is to argue until we reach a conclusion, right? So argue until you can say the thing that we need to show is that G is connected. Okay, so let's go through this whole process again, actually writing the proof this time. Prove that the sum of any two odd integers is even. So step one is write it in more formal language. So we would say for all integers, so for any a and b in Z, if a and b are odd, so we're adding two odd integers, then their sum, which is a plus b, is even. Step two is to suppose the if part. So we're going to suppose a and b are odd integers. Okay, step three is write the argument. Use definitions, use theorems, try to write an argument that, assuming this is true, it must be that this is true. We need to show that a plus b is even. Okay, so a and b are odd. So a and b odd means a is 2 times an integer plus 1, and b is 2 times not necessarily the same integer plus 1. So a is 2 times an integer plus 1, and b is 2 times an integer plus 1. So I said the word integer when I'm referring to k and j, but I haven't written it down yet, so I'm going to put that for some k and j in the integers. Thus, we can now try to figure out what a plus b is. A plus b, I'm going to use substitution. A is odd, which means it can be written as 2k plus 1. B is odd, which means it can be written as 2j plus 1. And then I combine like terms, right? So I have 2k plus 2j and plus 1, which is plus 2. And I have a 2 in every term, so I'm going to factor out a 2, and I have 2 times k plus j plus 1. All right, k and j and 1 are all integers, right? I defined k and j to be in Z. 1 is in Z. So when you add integers together, you get another integer. So 2 times an integer. A plus b equals 2 times an integer. So a plus b must be even. So let's just write a sentence that explains that logic. We'll say since k plus j plus 1 is an integer, a plus b equals 2 times an integer, and thus a plus b is even, which is what we needed to show. The then part of this statement is that a plus b is even. So often when you finish a proof, you put a little box and a check mark. Proved it.